Maybe you can share full screen.
Now, I don't know if I begin now or not because the time is.
It is not full screen, but you can make it full screen by pressing Ctrl and L. Yes, Professor.
Then now I begin. Do I begin?
Yeah, Professor.
Okay.
You can go on, please.
Okay, thank you. Okay, good morning, everybody, and thank you to the organizers to give me the opportunity to participate in this seminar.
Sorry, Professor, interrupting you. Could you please share your screen, full screen?
Now it's better.
Control L, I think.
Okay, it's okay.
No,
it's
not full screen at the moment. As far as I see.
Moment, please. Don't know how to. Sorry. Please.
Maybe you can use the Control and L at the same time.
Control
L. No, press L. Control L.
Moment, please. Now is okay now?
No, Professor. Please Control and L at the same time. Please. Control and L. Anyway, I think it is readable, your slide. You can go, Professor, please. Thank you.
Now it's okay?
It's not full screen, but I can read your slides, Professor. No problem. You can go, please. The microphone is yours now.
Yeah, but
thank you.
Okay. Moment, please. Okay. Well, I begin with the question is what the shape of a hanging chain? The answer is no, is the catenary. Here you fix the curve, the length of the curve, and also you fix the end points of the curve. And this is the equation of the catenary. The catenary is the model for the construction of arch. Why? Because here the forces on the curve are tangent to the curve. And then when we turn upside down the curve, then these forces, these tangent forces transforms into compression forces. And then this gives rigidity to the arch. This is equivalent to say that the catenary is the curve with the lowest center of gravity among of curves with the same endpoints and the same length. Okay, and now this is the shape of catenary. This is electric cable. In this case, it's different. It's not this curve is not a catenary, it's a parabola, because in this case, the curve is holding the rod of the bridge. This is a difference between both curves, between catenary and parabola. And now I ask, what is the two-dimensional problem? Now the initial data is a given closed curve and a given area. And then the question is, what is the shape of a hanging surface with this boundary curve and with this area?
Sorry, interrupting you, Professor Lopez.
Yes.
I'm seeing your fourth slide only. It's not moving in my screen.
The previous slide.
Maybe you can check the slide. I'm only seeing your fourth slide. It's not moving at the moment.
It's okay?
No. Still, the fourth slide is on the screen.
Sorry,
Maybe you can close and reshare. You can reshare, please, Professor.
Sorry.
Sorry, interrupting you.
It's okay now?
Can you move forward or backward, please?
Sorry?
Can you move the slide forward or backward, please? Thank you. It's correct now. Thank you, Professor.
Okay. Okay. And now, okay, the question is, what is the shape of a hanging surface? Okay. This is the energy of the surface. I explain why. This part is the weight of the surface. Z is the height with respect to a reference plane. In this case, is the plane of equation Z equals 0. Sigma is the density per unit of area. And in this part, this is the Lagrange multiply given by the prescribed area of the surface. And now I use calculus of variation. Because the problem is local, then I consider surfaces which are graphs of a function u defined in a domain of the xy plane. And now here I consider a variation of the surface. Phi is a function vanishing along the boundary of the domain. This is the energy. This is I assume that the density is 1. du is the gradient of the function u. And now I consider the critical point of the energy. And then this is now is in some sense is typical in calculus variation. This is the Lagrangian of the energy. And then this is the Euler-Lagrange equation of the surface. The subscript means the derivative with respect to the variable x and y. Okay. After a vertical translation, I assume that lambda is 0. Okay. And this part is the divergence of the gradient divided by this function. And now I can give a geometric interpretation of this equation. This part, the left-hand side, is two times the mean curvature of the surface. On the right-hand side, u is the third coordinate of the position of a point of the surface. And this part is exactly the third coordinate or the unit normal vector of the surface. And now this is the equation of the critical point of the energy. And then I call these surfaces singular minimal surfaces. The problem is possible that the problem has no solution because the problem of to find minimize is hard. Here, this is one example. I fix the boundary. The boundary is the unit cycle, and the area is 2 pi. And now I consider a uniparametric family of surfaces like this. Is the surface part? This is the boundary. The surface is a cone with this boundary, and the height is so the area is exactly 2 pi. And now I reduce the radius of the cone. I increase the height of the cone, and the surface is this annulus together the cone. And then the area is 2 pi. The boundary is the same, is the unit cycle, but the center of gravity goes to minus infinity. In this case, there is no minimizer of the problem. Of course, people could think that there are many cupula that don't satisfy the singular minimal equation. I mean, this equation. Okay, this is the ideal model from the mathematical viewpoint. But in architecture, there are other problems in the construction, not only about the design of the beauty, and also, for example, about the elasticity of the material. Okay, this is famous cupola, and here there are other using minimal surfaces, and here surfaces with constant mean curvature, because in this case, for the Eskimo, the igloo, the volume is fixed and the area must be minimum. Then the solution is the half sphere. Okay. And now I ask about example of singular minimal surfaces. For this, I consider two types of geometry: cylindrical surfaces and rotational surfaces. This is in this case, for cylindrical surfaces, V is the direction of the ruling of the surface, and then if you suppose that the surface is singular minimal surface, then the rulings of the surface must be orthogonal to the direction of the gravity, and this is the equation of the generating curve. In this case, this equation is exactly the equation of the Catenary. The Spanish architect Gaudí used Catenary art to construct corridors in different buildings. In this case, this is the Catenary curve. Okay, of course, you have to turn upside down the Catenary. Okay. For rotational surfaces, the result is, in some sense, is surprise, because people could think that the rotation surface, the rotation axis of the surface must be parallel to the gravity. Of course, this is one type of the solution. And there are two types of rotational surfaces and singular minimal surfaces. One case is that the rotational axis must be parallel to the gravity, and this is the equation of the generating curve. But also there are other kind of surfaces. In this case, the rotation axis is horizontal, in some sense opposite to the mind of the people who think about the cupola, because the people think the rotational axis must be vertical. But also there are rotational singular minimal surfaces where the axis is horizontal, and this is the equation of the generating curve. It is similar that the Catenary, but the only difference is that here appears the number 2, not 1, like in the Catenary. This is the description of the rotational surfaces of the first type, when the rotation axis is parallel to the gravity, and this is the shape of the curves. Okay, and also in this case is when the rotation axis is horizontal. This is the generating curve of the surface. This is the solution of this equation. In this case, the curve is defined in a bounding in a bounding interval, and the curve is asymptotic to the end of the interval, go to infinity. And this is, I think, this is the surface, the rotational surface. And then when we turn upside down the surface, then here I obtain the ideal model of the cupola. The difference is that here the rotation axis is horizontal. Now I ask about is it possible to use other surfaces to be useful to the construction of cupola, not being singular minimal surfaces, because rotational singular minimal surfaces are difficult to design, because we only have numerical approximation of the solution of the equation. This idea was thought by Gaudí, because Gaudí, in the construction of cupola, he thought that the solution is not easy in some sense. And then he used models of cupola to construct real cupola, in this case in the Sagrada Familia. Okay, but for people who think that there are two candidates to be model of cupola, no singular minimal surfaces, okay? One of the surface is I call Catenaria rotation surface. The Catenaria rotation surface is only to rotate a vertical catenary, okay? And the other, because, well, okay, why? Because if the catenary is the model for curves, people could think that is the model for the two-dimensional case. The other surface is the paraboloid. You rotate a vertical parabola. The advantage of paraboloid is because the paraboloid is given by polynomial, and then it's easy to construct from the architect viewpoint. Both surfaces are not singular minimal surfaces, okay? And then I ask, what is the difference between the center of gravity with respect to the ideal model? And then this is the equation of the rotational singular minimal surface. Okay, and then here I impose the initial condition. This is the lowest point of the surface, and this condition means that it's orthogonal to the rotation axis. Okay, and then I fix the boundary, and also I fix the area of the surface, and then I compute the height of the center of gravity. And now I do the same with the other two candidates. The first candidate is the Catenaria rotation surface. This is the profile of the surface, and then I impose the boundary condition. I compute the area. It's possible to compute the area explicitly, and also the height of the center of gravity. Okay, and the same with the paraboloid. This is the parabola. I impose the boundary condition. I compute the area, and also I compute the center of gravity. And now I want to compare the center of gravity of the three surfaces: the ideal model, the Catenaria rotation surface, and the paraboloid. And then this is the table of comparing of these values. Here there are different radius of the boundary. This is the area of the surface. These data are given, are prescribed. This is the height of the center of gravity of the ideal model, and here of the Catenaria rotation surface and of the parabola. If you look, the difference is nothing, or is very, very, very small. How to measure the difference? Now here is the percentage of the difference between the height of the center of gravity with respect to ideal model with respect to the height of the surface. And then the percentage is less than 1%. 1%. This is the computation for the Catenaria rotation surface. In this case, is for the paraboloid. Even more, you look that the height of the center of gravity of the paraboloid is less than the Catenaria rotation surface. It's curious because in the one-dimensional case, the Catenary, the height of the center of gravity is less than the parabola, because the Catenaria is the ideal model. Then the conclusion is, of course, the center of gravity of the model is less, but of the paraboloid is less than the Catenary rotation surface. And the deviation is less than 1%, and is better in the case of paraboloid. Also, this deviation is no increase with respect to the area of the radio, because here increase until some value and after decrease. Okay, and here you can look the Catenaria rotation surface, the ideal model is the blue color, and the paraboloid. And be careful because here the difference between the lowest point is high, but we are comparing the height of the center of gravity. It's not the lowest point of the surface. And now, to finish the talk, I asked the problem about the stability of the singular minimal surfaces. In this case, about cylindrical singular minimal surfaces. The problem is motivated by the theory of surfaces with constant mean curvature, because if you consider a cylinder of given radius, if the length is large, then the surface is unstable, and then in this case it appears liquid drops. And then I asked the same problem for cylindrical singular minimal surfaces. If you recall, the generating curve is the Catenary, okay? And then this is the parametrization of the surface. A is the amplitude of the surface, and L is the length of the surface. And then the problem is I fix A, then it is possible to find L such that if L is bigger, then the surface is unstable. Okay. The definition of stability is that the second derivative of the energy is non-negative. Okay. And now we need to compute the second derivative, and then the second derivative is this integral. Okay, where L is the Jacobi operator is given by this part. Okay, this is the Laplacian on the surface, and this is the gradient on the surface. Phi is a function vanishing along the boundary. A is the second fundamental form. Okay, this expression is difficult to compute, but if now I consider phi by separation of variable, then this part reduces a lot. This part is exactly this function where h is the hyperbolic cosine, is the generating curve of the surface. Okay, and now I had to impose that this function vanishes along the boundary, and then for t is the length of the surface. Then I consider the sign of this function. This g vanishes on t equals 0 and t equals L, and then I put in this integral, okay? And then if this is the integral, this is minus, this part is positive, because I ask about instability, I need that this part is positive, okay? And now the other function f, I consider a translation of the hyperbolic cosine, okay? To vanish along the boundary. And now I put here, and now I have to compute this integral, okay? This integral is separated in two terms. One term depends on the function of the value a, and here of a and L. This is the explicit computation of the integrals. The second here, if you fix a and L go to infinity, then this part go to 0, okay? And then this is the theorem. The theorem says that if you fix the amplitude after this value, then if the length is bigger, then the surface is unstable. Okay? The proof is the following. After this value, the first integral, the first integral, this is the function. If a is bigger, then it's positive. Okay? But the second integral, if L is big, then it goes to 0, and then when you sum is positive. For this reason, the surface is not stable. Okay, I finished the talk. Thank you.
Thank you very much for your interesting and stimulating speech, Professor.